Okay, consider an application that lets user log in with a username and a password. If a user submits the username winner and the password blue cheese, the application takes the credential by performing the following SQL query. Select from users where the username is winner and the password is blue cheese. If the query returns the details of a user, then the login is successful. Otherwise, it is rejected. Here, an attacker can log in as any user without a password simply by using the SQL command sequence like with 2 dashes. To remove the password check from the where clause of the query. For example, submitting the username administrator and the 2 dashes and the blank password and the blank password results in the following query, like with empty 2 apostrophes. Then this query returns the users whose name is administrator and successfully logs the attacker in that user. Retrieving data from the database tables. In cases where the results of the SQL query are returned within the application's responses, an attacker can leverage a SQL injection vulnerability to retrieve data from other tables within the database. This is done using the union keyword, which lets you execute an additional select query and append the results to the original query. For example, if an application executes the following query containing the user input gifts, select name description from products where category gifts, then an attacker can submit the input union select username, password from users and the 2 dashes. This will cause the application to return all usernames and the passwords along with the names and the descriptions of products. Let's talk about blind SQL injection vulnerabilities. Many instances of SQL injection are blind vulnerabilities. This means that the application does not return the results of the SQL query or the details of any database's errors within its responses. Blind vulnerabilities can still be exploited to access unauthorized data, but the techniques involved are generally more complicated and difficult to perform. Depending on the nature of the vulnerability and the database involved, the following techniques can be used to exploit blind SQL injection vulnerabilities. Here, you can change the logic of the query to trigger a detectable difference in the application's response depending on the truth of the single condition. This might involve injecting a new condition into some Boolean logic or conditionally triggering an error such as a divide by 0. Also, you can conditionally trigger time delay in the processing of the query, allowing you to infer the truth of the condition based on the time that the application takes to respond. You can trigger an out-of-bound network interaction using WAS techniques. This technique is extremely powerful and works in situations where the other techniques do not. Often you can directly exfiltrate data via the out-of-band channel, for example, by placing the data into a DNS lookup for a domain that you control. Second order SQL injection. First order SQL injection arises where the application takes user input from an HTTP request, and in the course of processing, that request incorporates the input into a SQL query in an unsafe way. In second order SQL injection, also known as stored SQL injection, The application takes user input from an HTTP request and stores it for future use. This is usually done by placing the input into a database, but no vulnerability arises at the point where the data is stored. Later, when handling a different HTTP request, the application retrieves the stored data and incorporates it into a SQL query in an unsafe way. Second order SQL injection often arises in situations where developers are aware of SQL injection vulnerabilities and so safely handle the initial placement of the input into the database. When the data is later processed, it's deemed to be safe since it was previously placed into the database safely. At this point, the data is handled in a safe way because the developer wrongly deems it to be trusted. Examining the databases. Some key features of the SQL language are implemented in the same way across popular database platforms, and so many ways of detecting and exploiting SQL injection vulnerabilities work identically on different types of database. However, there are also many differences between common databases. This means that some techniques for detecting and exploiting SQL injection work differently on different platforms. For example, syntax for string concatenation, comments, budget, queries, platform-specific APIs, error messages. Following initial identification of a SQL injection vulnerability, it's generally useful to obtain some information about the database itself. This information can often pave the way for further exploitation. You can query the version details for the database. The way that this is done depends on the database type. So you can infer the database type from whichever techniques works. For example, on Oracle, you can execute select from version. You can also determine what database tables exist and which columns they contain. For example, on most databases, you can execute the following query to list the tables. It's select from information schema tables. How to prevent SQL injection. Most instances of SQL injection can be prevented by using parameterized queries, also known as prepared statements, instead of string concatenation and within the query. The following code is vulnerable to SQL injection because the user input is concatenated and directly into the query. String query is like this, and then this code can be easily written in a way that prevents the user input from interfering with the query structure like this. And the parameterized queries can be used for any situation where untrusted input appears as data within the query, including the where clause and the values in an insert or update statement. They can be used to handle untrusted input in other parts of the query, such as table or column names or the order by clause. Application functionality that places untrusted data into those parts of the query will need to take a different approach, such as whitelisting permitted input values or using different logic to deliver the required behavior. For a parameterized query to be effective in preventing SQL injection, the string that is used in the query must always be a hard-coded constant and must never contain any variable data from any origin. Do not be tempted to decide case by case, other an item of data is trusted, and continue using straight concatenation and within the query for cases that are considered safe. It's also too easy to make mistakes about the possible origin of data and for changes in other code to violate assumptions about that the data is tainted.